Here we have 4 different objects, all sitting on frictionless planes of the same angle and height. They all have the same mass, and all of these round objects have the same radius, r. And we'll say this box has a side 2r. Dimension of its side is a square box. Now, if each one of these objects starts at the top of the ramp and then goes down to the bottom, we'll say that all of the round objects roll without slipping. And the plane for the box is frictionless. So at the bottom of the ramp, which object will have the fastest linear speed? And then we want to know which has highest moment of inertia. You're going to ignore the block for that one because it's not rotating. And then 3, which has the highest rotational kinetic energy at the bottom? And also we'll say which has highest total kinetic energy. So we'll look at the answers and then we'll work the math out for it. Now, one of the fastest linear speed at the bottom is going to be the box. The one with the highest moment of inertia is going to be the hoop. The one for the highest rotational kinetic energy is also going to be the hoop. And the one with the highest kinetic energy total is actually, they all tie. All the objects and not just the round ones. So now we'll work the math out for this. Well, let's call the top state 1 and the bottom state 2. We see that there's no friction doing work here. Then what is conserved from the top to the bottom? Energy. So states 1 to 2, energy is conserved. And we will actually put some numbers in here just so we can prove out theta doesn't actually matter. Say h is 1 meter and mass is 10 kilograms. Okay, so for 1, fastest speed at the bottom. Well, we know that energy at 1 equals energy at 2, mgh. At 1, we only have potential energy, and then at 2, we only have kinetic. Equals the translational, 1/2 mv squared, plus the rotational, 1/2 I omega squared. But first we need to figure out I for each of these things. So 2, for moment of inertia, we know that for the hoop, then I equals m r squared. And I guess we should be given r. R equals 0.1 meters. We'll say that. So hoop I equals m times r squared equals 0.4 kilograms times meters squared. Then for the box, we'll say box is 0 because it's not rotating. Then for the disk, I equals 1/2 mr squared equals 0.2 kilograms times meter squared. And then for the sphere, I equals 2/5 mr squared, which equals 0.16 kilograms times meter squared. So we can see that the hoop definitely has the greatest there. So we'll actually say hoop. Let's be red. Okay, so now we also need to get rid of the omega and change everything to V. So we know that omega equals V over R. Okay, so we'll use that in here. So we'll have, for the box, mgh equals 1/2 mv squared plus 0, because the box does not have any rotation. So it's just got the 1/2 mv squared. So then these cancel. V equals square root of 2gh, which equals 4.43 meters per second. So then the hoop will have mgh equals 1/2 mv squared plus 1/2 I omega squared, which is going to be 1/2 m r squared times v over r squared. So these r squares cancel, and we just get m v squared. So v equals square root of gh, which equals 3.13 meters per second. So that is definitely less than the box. We'll look at the other ones. Then the disk, we've got mgh equals 1/2 mv squared plus 1/2, and here the I for the disk is 1/2 mr squared. So 1/2 times 1/2 mr squared times v over r squared. So this is v equals square root of 4gh over 3, which equals 3.62 meters per second. So more than the hoop, but still less than the box. Then finally, we look at the sphere. mgh equals 1/2 mv squared plus 1/2 times at moment of inertia, which is 2/5 mr squared times v over r squared. This simplifies to v equals square root of 10gh over 7, which equals 3.74 meters per second. If we rank these speeds, then speed for box is greatest, and then speed for sphere, then speed for disk, and then speed for hoop. So you see, this is kind of inversely proportional to the moment of inertia, because for moment of inertia, we had I hoop was greater than I for the disk, which was greater than I for the sphere, because they both start at the top with the same amount of potential energy. So at the bottom, some of that potential energy goes into rotational kinetic and some goes into translational kinetic. So just depending on what proportion of the energy goes into each type, then that will dictate what the speed is going to be. So the one with the highest kinetic energy of rotation is going to be proportional to this 1/2 I omega squared. So for 3, we said that was the hoop. So for 3, we know kinetic energy for rotation equals 1/2 I omega squared equals 1/2 times I v over r squared. So if we do the math for this in the hoop, so we know v because we figured it out here in part 1, and then we know I because we figured that out for part 2. So the hoop is 49 joules. Then the disk equals 32.8 joules. The sphere equals 28 joules, and then the box is not rotating, so box is 0. As far as rotational kinetic goes. So the hoop wins for that. Now, which has the highest total kinetic energy? It's going to be a tie, because the energy at the beginning equals the energy at the end. So if they all started out with the same energy, they all end with the same energy. Potential converts to kinetic, which is different types of kinetic.